Hello, everyone. Welcome to our today's quantitative analysis session. Today, I would want us to look at probability theory. Remember, it is our crash revision program, what we call block release. And this probability theory, I would want us straight away to get into questions, and I would want us to look at November 2019. November 2019, question number 1, boy. November 2019, question number 1, boy. I hope all of you have bought our revision kits. If you haven't bought, this is our number. Get in touch with us and we shall be able to give you revision kits that are good for your revision. So you're told November 2019, quantitative analysis, November 2019, question number 1B. Question number 1B. November 2019, question number 1, boy. We are told there 6 consultants work for XYZ Company Limited. A consultant has a 20% chance of being absent from work in a given day. The company needs to establish the probability of more than 2 consultants being absent from work. More than 2 consultants being absent from work. So compute the above probability of absence, assuming number 1, a binomial distribution, and then number 2, a Poisson distribution. So we start with the first one, a binomial distribution. So we have here a binomial distribution. Ladies and gentlemen, remember that a binomial distribution is that model that is used to compute probabilities of events involving experiments with exactly how many outcomes? 2 outcomes. Like in this question, it is either a consultant is present or absent. There are no 3 ways about it. It's only 2 ways: present or what here? Absent. So it's a binomial distribution. It's a Bernoulli distribution. And if it's a Bernoulli distribution, ladies and gentlemen, if you recall, there is a formula that we have here. Probability of capital X being equal to small x will be equal to what here, somebody? This one here will be equal to n combinations x, p raised to x, q raised to what here? N minus x, like that. This is the n combinations x. N combinations x. Basically, it is found in your calculators. It is found in your calculators. It is found in your calculators. That is what you need to know. Once you have your calculator, you'll be able to see NCX or NCR somewhere there. Just somewhere close to shift in your calculator, shift or alpha. You'll be able to see NCR function there. So, ladies and gentlemen, what these people want us to do, or rather even before we read the question, we have this P. The probability given in the question, the probability of a consultant being absent is 20%. 20% is 0.2. So once you give me 0.2 probability, then getting the other probability, which is our Q, is a walk in the park. Why? Because I know that the 2 must always add up to 1. Meaning, ladies and gentlemen, that Q will be 1 minus 0.2, which will be equal to 0.8. The 2 must always add up to 1. P plus Q is always equal to 1. That is very important. N is my sample size. We've sampled the 6 consultants. So now, ladies and gentlemen, with this, I will very easily answer whichever question that this examiner wants us to get. Like here, they want us to give them the probability that more than 2. So probability that more than 2. Probability of more than 2 means what here? This means probability of X being equal to 3. Probability of X being equal to 4, 5, or what here, somebody? 6. So it means that you go evaluating the probability of each of these events, and then you do what? You add them. Now, ladies and gentlemen, using this concept of mutually exhaustive events, if you look at all the possible events, ladies and gentlemen, that we have, the outcomes that we have, there are many types of outcomes here. There is that scenario that we may not get any consultant being absent. Probability of X being equal to 0. Then we have probability of X being equal to 1. Then we have probability of X being equal to 2. And then now we have all these events. Now, if they are collectively exhaustive, we expect that when you add all those events, ladies and gentlemen, from probability of X equals to 0, all the way to probability of X equal to 6, we need to have all those probabilities summing up to what? To 1. Meaning, ladies and gentlemen, that this particular one here can also be obtained by taking 1 minus the events which are now not here. 1 minus the other events. Remember, the other events are which events here, which are not now here. It's probability of X being equal to 0, or 1, or what here, or 2. Allow me to repeat, ladies and gentlemen, probability of more than 2 means that we start from exactly 3. So it is probability of either 3, 4, 5, or what here, 6. Now, these are too many events. When you get too many events that you would want to evaluate their probabilities, always think about the complementary. What do I need to include onto this to complete the entire sample space? To complete the entire sample space, start, of course, with what here. Start, ladies and gentlemen, to complete the entire space. Let me make this clear. Let me make this clearer. Let me make this clearer. To have the entire sample space, the entire sample space here is probability of X being equal to 0, or 1, or 2, or 3, or 4, or 5, or 6, which will be equal to what here, somebody? Which will be equal to 1. Now that they want just from here to here, right? So they want probability of X being equal to 3, or 4, or 5, or 6. Then if I make whatever they want the subject of the formula, this is what I'm going to get. It will be 1 minus these other events, minus probability of X being equal to 0, or 1, or what here, or 2, like that. Very important for us to be able to appreciate that. Now, ladies and gentlemen, the moment you give me that particular model, it will be very easy for me to get these probabilities that we have here. So we'll start with probability of X being equal to 0. Remember, already we have our model. Our model is the one that goes like this: n combinations X, P raised to X, Q raised to n minus X. So our n, ladies and gentlemen, here is 6. So 6 combinations 0. P, I hope you remember our P was 0.2. So 0.2 raised to this X, which is 0, times Q is 0.8. 0.8 raised to n. This is our n. So it is 6 minus our X here, which is, ladies and gentlemen, remember that these two powers, the two powers here must always add up to what here? To this n. So once you give me one of the powers, then the other power, I'll easily get it there as a balancing figure. After all, we are saying that the two powers must always add up to what? The two powers must always add up to n. So then, ladies and gentlemen, the moment I have this, I will very easily give you these 6 combinations 0. What are 6 combinations 0? In my calculator, this is my calculator. So I'll say on there, press 6. I hope you are able to see the combinations just close to shift, just underneath alpha. So I'll say 6 combinations 0, this one here. And then I'll say times 0.2 raised. I hope you're able to see the raised. In some calculators, raised is like this. So raised to what here? To 0. Then I'll say times again 0.8 raised to power what here? Power 6. So ladies and gentlemen, what figures am I getting here? I'm getting 0.2621. So this is the probability of the first event. Take on probability of the second event, where X equals what here? Where X equals 1. So come and give us the probability when X equals 1. Remember, we are using this general formula. It will be 6 combinations 1 times 0.2. Remember now X is 1. So then 0.2 is raised to X. So 0.2 raised to power 1 times our Q is 0.8. Remember these figures, I gave them to you up there. So 0.8 this time around will be raised to a new power. How do I get the new power? I know that the two powers must always add up to this. It means that the power of Q will be 5. So ladies and gentlemen, again, armed with your calculator, come right away here, press 6 combinations 1, right? Times 0.2 raised to power 1 times 0.8 raised to power 5, which at the end of the day will give us 0.3932. From there, ladies and gentlemen, we have the last event. The last event is probability of x being equal to 2. Probability of x being equal to 2 will go like this: 6 combinations x, where our x is 2. So 6 combinations 2 times 0.2 raised to power x, where our x is 2, times 0.8 raised to our new power here. Remember the fact that the two powers must always total to 6 here, must always total to the n that is here. So meaning, ladies and gentlemen, that this one here will be 4. So then what do we have here? We have 6 combinations 2 times 0.2 raised to power 2 times 0.8 raised to power 4, So then at the end of the day, we'll end up getting 0.2458 like that. Ladies and gentlemen, or means what here? That come and give us a consolidated total figure. Add them. So this gives us 0.2621 plus 0.3932 plus 0.2458, which will give me 0.9011. Remember, that is not the probability that they wanted us to get. If you remember, what they wanted us to give them here is 1 minus that block figure that we have just found there. So our probability, if I could just rub this a little bit, our probability for more than 3, will be, ladies and gentlemen, this will be 1 minus 0.9011, which will end up giving us 1 minus 0.9011, which gives us 0.0989, like that. So this answer is 0.098 what here? 89, like that, about 9.89%. So that is it, ladies and gentlemen. I hope that is clear. The most important thing is to appreciate that they wanted us to give them the probability of getting more than what? More than 2 being absent. So more than 2, we start counting from 3, 4, 5, and 6. We realized that those were too many events. We went for the complementary thing. Ladies and gentlemen, the next question here, the next question, which is Roman 2, is a Poisson distribution, the same data, but this time around, ladies and gentlemen, they want us to solve using a Poisson what here? Using a Poisson distribution. Still, it is probability of x being more than what here? More than 2, which will be probability of x being equal to 3 or 4 or 5 or 6, which again calls for the complementary thing. This could be too many at times. It's important for you to understand that complementary, to complete. So events to complete, so it will be 1 minus the missing events, which basically will be probability of x being equal to 0 or 1 or what here? Or 2. Great, I like this. So this time around, they want us to evaluate these, ladies and gentlemen, using what here? Using a Poisson distribution. If it is Poisson distribution, I know how this distribution looks like. Probability of capital X being equal to small x will be equal to E raised to negative lambda raised to x, all over what here? X factorial, all over x factorial. So then what you need to do, ladies and gentlemen, is to get the probability of each one of these. The very best, because this E will apply to each one of them, is to factor it out. So probability of x equals 0 or 1 or 2 using this Poisson will be equal to E raised to negative lambda. Remember that lambda is the mean. Lambda is the mean. Lambda is the mean. In this question, they never gave us the mean. Remember, in our normal class, we said whenever the mean is not given, to get lambda, we normally talk of n what here? We normally talk of NP. To get lambda, we normally talk of NP. NP. So, ladies and gentlemen, my lambda here will be equal to N6 times this probability. If you recall, our P was 0.2. So 6 times 0.2 gives us what? 6 times 0.2 gives us 1.2, like that. This gives us 1.2. Once I have that, now I'll be able to apply this other formula very easily. Very easily. Ladies and gentlemen, this is what I will do. Once I have my mean, I hope you have taken this down. Once I have my mean there, now I will be able to get this. So I'll come and factor out e raised to negative lambda. E raised to negative lambda out. Right, into, I can see lambda. Lambda here is 1.2 raised to the first x figure, which is what here? 0. 0. All over 0 factorial. So I'm factoring out this e because it's applicable to each one of them. But now inside brackets, I'll be having this lambda raised to that all over x factorial. So of course, after that, I'll come and capture this factor for 1. So plus the same. The mean raised to 1 raised to x, which is 1, all over 1 factorial. All over 1 factorial. Plus, ladies and gentlemen, we have here 1.2 raised to power 2, all over what here? 2 factorial. All over 2 factorial. So please go ahead and evaluate this, all of it at once, using your calculator. Remember, you are getting these classes here from RCM. RCM Online College. This is our number, 0719 525,000. 0719 525,000. We are a great college, especially for online tutorials. If you want videos, if you want the very best revision books, the very best study text, please talk to us today. This is our number, 0719 525,000. Talk to us today. Today. Great. So please get out your calculator. When you get out your calculator, try to see where E is. In my calculator, E is the third button from the top, where you are able to see on. This button here, when you go down, you'll be able to see in. You'll be able to see in. It's ln, natural logarithm, Napierian logarithm. So on top of it, we'll be able to see e raised to negative what here? E raised to x, E raised to x. So then it's in yellow, meaning that I have to press shift first. So shift E. Once I press shift E, what I need to do is to come, don't raise again. Don't raise again. What I need to do is to come and say minus 1.2, because you know that e raised to x is coming as a raised function. If you try raising again, you'll end up getting a syntax error. So I'll say equals first. I'm able to see 0.30 something times into brackets. We have 1.2 raised to power 0 divided by x factorial. Divided by x factorial. Just beneath your shift. Beneath your shift, you'll be able to see x raised to minus 1. On top of that, x raised to minus 1, you'll be able to see x with an exclamation mark, factorial. So then I'll press here, divide by 1, shift, that factorial, because it is in yellow, I have to shift. Plus, ladies and gentlemen, 1.2 raised to 1, divided by, I have to go back a little bit. This is supposed to be 1.2 raised to 0, all over 0 factorial. All over 0 factorial. So shift like that. Plus, we have 1.2 raised to 1 divided by 1 factorial plus 1.2 squared divided by 2 factorial. Close brackets, you say equals. So when you say equals, what are you able to get here? I'm getting 0.8795, like that. But please, once you get this figure, remember what these people want us to get. They want us to give them Probability of more than what here? Probability of more than 2. Probability of more than 2, then this one here will be 1 minus this consolidated figure, which is 0.8795. So 1 minus answer, which will be 0.1205, like that. That is the answer. You can see, of course, the two models are not giving us the same answers. Not giving us the same answers. So that is the end of that question. Please remember, I'm urging you to buy our videos and our study materials, our KASNEB's RCM study materials, by calling this number 0719 525 1000. 0719 525 1000. So we look at December 2013, question number 2A. December 2013, question number 2A. Quite a short one. If you don't have it, you can even copy it. But most importantly, you need this book. You need this book. And if you want to get it like today, please just call us through this number 0719 525 1000. 0719 525 1000. So you're told here, an electric utility company has established that the weekly number of occurrences of lightning striking a transformer is Poisson distributed, underscore the words, Poisson distributed, with a mean of 0.4. So they want us to give them the probability that no transformer will be struck by lightning in a week. So ladies and gentlemen, it's a Poisson distribution. And if it's a Poisson distribution, then the very first thing we need to do is to come and jot down the formula. Probability of x being equal to x. Probability of x being equal to x will be equal to, if it's Poisson, remember, it will be e raised to negative lambda, lambda raised to x, all over what here? X factorial, all over x factorial. So remember that this lambda is our mean, which has been given to us in the question. Ladies and gentlemen, remember, amongst the many probabilistic distributions that we have, Poisson distribution is among the few that is fully defined by the mean alone. Once you give me the mean alone, then I'll be able to give you Poisson probabilities. I'll be able to give you Poisson probabilities. So ladies and gentlemen, what do they want us to give them here? Number one, they want us to give them the probability that no transformers will be struck by lightning in a week. So basically probability, this is number one, of our x being equal to 0. So then, ladies and gentlemen, this will be e raised to negative lambda. Our lambda here is 0.4. And then we have 0.4 down there raised to x. X that you would want to work with is 0 here. So raised to 0 all over x, which is 0 factorial, which is 0 factorial. So ladies and gentlemen, what we have here, so get your calculator. Remember where your E is. My E is on the third line. From this on button, third line, I'll be able to see e raised to x, which is in yellow, which is yellow in color. If it's yellow in color, it means I'll have to say shift. So shift E. Shift E. Remember the way it is there, it is already raised. If you try raising again, you will end up getting a syntax error. You'll end up getting a syntax error. So don't raise again, simply write minus 0.4, just like you're subtracting direct. Say equals times, we have 0.4 here, raised to 0, divide by 0 factorial. I hope you're able to see factorial just below the shift function. And you will need to shift. So shift, you need to shift because it's yellow in color. Shift factorial, that exclamation mark. So then what are you able to see? The answer here is 0.6703. That is it. 0.6703. That is it. I hope you're following. Please don't forget to buy our video tutorials, our videos, our online classes at very reasonable fees by calling this number 0719 525,000. 0719 525,000. So ladies and gentlemen, let's look at number 2. Number 2, what do we have? In number 2, they want us to give them the probability. They want us to give them the probability that at most 2 transformers will be struck, at most, probability that at most 2 transformers, at most 2 transformers will be struck, meaning that the 2 that they have mentioned here is the most, is the highest figure. So it is 2 or less at most. So then, ladies and gentlemen, what do we have? This will be probability of x being equal to 0 or 1 or 2. And really, these are not many events that we should start thinking of a complementary. 3 events. What I'll need to do is to come and simply evaluate them. And how do we evaluate this? Remember, it's very easy. Come and put this e raised to negative 1.4. E raised to negative 1.4. And then into brackets, what do we have here? You can see we have lambda raised to x. So lambda is the mean, which is 1.4. So 1.4 raised to the first x figure, which is 0, all over the first x figure factorial, plus the same arrangement, but this time round x is 1. So raised to 1 all over 1 factorial plus 1.4 raised to 2 all over 2 what here factorial like that. And you get out your calculator. You get out your calculator. The moment you get out your calculator, you'll be able to get this thing very easily. So first of all, E. So we have shift E minus 1.4. You say equals first. And then we have times open bracket. We have 1.4 raised to. I hope you're able to see where the raised is. Raised to 0 divided by 0 factorial divided by 0 factorial plus the second term is 1.4 raised to 1 divided by 1 factorial divided by 1 factorial plus 1.4 raised to power 2 raised to power 2 raised to power 2 divided by 2 factorial divided by 2 factorial equals. So what I'm able to get here, ladies and gentlemen, the final answer is 0.8335. 0.8335. And that is it. Quite an easy thing. A Poisson distribution. A Poisson distribution. Please don't forget to procure our online content, our online videos by calling us today, RCM online call it today, which is 0719 525,000. Call us today to book our videos and what year books, our videos and books.
Good. So question number 3. Question number 3 is May 2017, question number 2A and B. For those of you who have got our revision kits, you simply go to probability theory, question number 7. Probability theory, question number 7 of our revision kit. If you would want to buy the revision kits, don't forget, this is the phone number, 0719 525,000. Also, we have videos and study books available for you at very reasonable prices. So we are told here to highlight 4 properties over a binomial experiment. Part A, highlight 4 properties over a binomial experiment. The one that I will never forget, ladies and gentlemen, is that a binomial experiment has got what here? 2 possible outcomes. 2 possible outcomes. Success, stroke what here? Failure. Number 2, any binomial experiment has got a finite number of trials, n. Finite number of trials, n. Very important. This probability of success, P, is known in advance and will remain constant. Is known in advance and will remain constant. And then, ladies and gentlemen, we have the concept of independence of the trials. The probabilities, of course, in this case here, from one trial to another trial are what here? Independent. They are independent. They are independent. They are independent. I hope I've given you 4. I've given you 4. Very important. Look at part B of this question. Part B, Viwanda Limited is a company that operates in the printing industry. The company has a total of 30 machines. So N is 30 machines that operate a 24-hour cycle. the probability of a machine breaking down on any given day is 0.015. So number one, they want us to give them the probability that exactly 4 machines break down in a given day using Poisson distribution. Using Poisson distribution, ladies and gentlemen, I know the formula. I know that P probability of X equals to small x will be equal to E raised to negative lambda, lambda raised to X, all over X factorial. And if you remember very well, the key thing that you need for you to be able to evaluate Poisson probability distribution parameters is the mean. You need the mean, which is our lambda. And our lambda, ladies and gentlemen, here is what here is NP. Our lambda is NP. Our lambda is NP. So in this particular case, our number of trials, we have 30, our N is 30, and the probability given here is 0.015, like that. So which at the end of the day will give me 30 times 0.015, which gives me 0.45. 0.45. Ladies and gentlemen, the moment you have given me really this mean, then automatically I'll be able to give you whatever probability, Poisson probabilities that you will be needing. So like now here, number one, they want us to give them probability that exactly 4 machines will break down. So probability of X being equal to 4, then these will be equal to E raised to negative lambda, so raised to negative 0.45, following this. So lambda down there raised to X, X which is what here 4, all over 4 factorial, all over 4 factorial, all over 4 factorial, like that. So then what you will need, ladies and gentlemen, right away here is your calculator. So your calculator, tell us there E. E is there, minus 0.45 times 0.45 raised to power 4, divided by 4 factorial. I hope you are able to remember where the factorial is. Divided by 4 factorial, which at the end of the day gives us quite a very small probability, which has got 3 zeros on the negative side, left-hand side, and then we have 1.089. So we have 1089 like that. Of course, I'll write the 3 zeros on the left-hand side, and then I'll plug in the decimal. That is the probability. A very small probability. A very small probability. Very small probability. Very small probability. So that is the answer to number 1. Answer to number 1. And then now we go to number 2 straight away, where they want us to evaluate the same probability, but this time around, ladies and gentlemen, using what here? Binomial. Using binomial. This time around, using the binomial probability distribution. This time around, using the binomial probability distribution. Binomial is very easy. It is n combinations x, x or rather p raised to x, q raised to n minus x. So probability, I'm moving quite fast because I know now you have become accustomed to this. This now is quite simple to us. So probability of x being equal to 4 will be equal to n. Ladies and gentlemen, n here is 30. Combinations x parameter is 4. And then we have probability of our success, which is 0.015, 0.015 raised to x, which is 4. And then we have q. I forgot to tell you that if p is 0.015, then q, given that the 2 must always add up to 1, to get q, what I need to do is to come and take 1 minus 0.015. 1 minus 0.015, which is 1 minus 0.015, which is 0.985. 0.985, like that. So now, ladies and gentlemen, the moment I've got those 2 parameters, I have already factored in p here. So I know that my q is 0.985 raised to n minus x. Now listen, n is 30, x is 4. When you subtract the 2, you should get 16, no, 26, 26. Now, ladies and gentlemen, listen here, listen here. The most important thing is for you to know that this power has to be the complete completing complementary. Why the two powers added together must always add up to this 30. So meaning that to get the new power here, simply take 30 minus this 4, 30 minus 4. So in this case here, we have what there? We have 26 like that. We have 26 like that. So ladies and gentlemen, straight away come and talk of 30 times, not times, but combinations. So we have 30 combinations, 30 combinations, 30 combinations 4 times 0.015 raised to power 4 times 0.985 raised to power 26, raised to power 26, which at the end of the day, again, gives us a very small probability, very small. So it's 4 zeros on the left because of negative 0.4. And then we have 93, 66. So between the two zeros, what do we have there? We'll put a decimal there, or you count the mother tongue with 1, 2, 3, 4. You still end up getting the same place, decimal place. Of course, you can see that the two models are giving us very low probabilities. But of course, the model that I will vote for as a model that has given me a proper, an accurate figure will be Poisson. Poisson becomes very appropriate when n is very big and the probability of success is very small. You can see probability is 0.0. When the probability of success is very small and the n is going up there to large samples, 30 and plus, then straight away, Poisson becomes what here? The most ideal, becomes the most ideal. So please don't forget to buy our videos. Don't forget to buy our books. Please, if you would want to buy any of our products here, call this number 0719 525,000. 0719 525,000. Okay, so let's continue. Ladies and gentlemen, I would want us to pick another question on this binomial. Now, this should be the last one for binomial, right? December 2014, question number 5B. December 2014, question number 5B. December 2014, question number 5B. We are told a survey was conducted in Pamoja village to establish the proportion of households that were affected by a certain pandemic. The results indicated that 40% of the households in the village were affected by the pandemic. So P is 0.4. A sample of 6 households was randomly selected from the village. So our N is what here? Our N there is 6. So the probability that only one household was affected by the pandemic, ladies and gentlemen, this probability is too huge, 40%. And given the fact that we have only 2 possible outcomes, it's either you are affected or not affected, then the better model here to use to approximate these probabilities, to ascertain these probabilities, will be the binomial model, So number 1, so the binomial model, probability of x being equal to x, of course, is n combinations x, p raised to x, q raised to n minus x, like that. So ladies and gentlemen, our n here is, or rather they want us to give them probability of x being exactly equal to 1. So then our n here is 6, 6 combinations 1. So P, already P is here, 0.4 raised to power x, which is 1. And remember that if P is 0.4, then Q will be 1 minus 0.4, which is 0.6, like that. So Q, I'm trying to plug in, Q here is 0.6 raised to the balancing power. Balancing power, remember the 2 powers must always add up to the n. So the balancing power then here will be 5. 1 plus 5 is 6, like that. So please get out your calculator to be able to evaluate this particular probability that the examiner wants us to get. So then these will be 6 combinations 1 times 0.4 raised to 1 times 0.6 raised to 5 equals, which gives us 0.18. 66, 0.1866. That is the end to that particular first requirement, which wanted us to give them the probability of exactly one household. The probability of exactly one household was affected. So that is it. So now we go to the second. We go to the second question, still under December 2014. Exactly 2 households were affected. So probability of X being equal to 2 like that. So then these will be N still stands, 6 combinations X. X is 2. P, which is 0.4, 0.4 raised to X, which is 2. 0.6, which is my Q, raised to the balancing power. The balancing power here will be 4, given the fact that the 2 added together must add up to what here? To 6. So if that is the case, ladies and gentlemen, here we have 6 combinations, 2 times 0.4 raised to power 2 raised to power 2 times 0.6 raised to power 4. So then these at the end of the day gives me 0.31104 like that. That is the answer. So Roman 2, we are done with it. So now we go to Roman 3. Roman 3. This was Roman 2. So we go to Roman 3. So under Roman 3, what do we have under Roman 3? Under Roman 3, ladies and gentlemen, what we have under Roman 3 is quite interesting. Roman 3, they want us to give them the probability that at most 2 households were affected by the pandemic, at most 2. So 2 is the most, 2 is the highest. Then these will be equivalent to saying probability of X is 0, or probability of X is 1, or probability of X is 2. Fortunately, we happen to be having probability of X equals 0. No, we don't have that. We have to look for this. The one that we have is 1. At least this one here, we have it. Right? So in this case here, probability of X equals 0. Then this we have here 6. I'm following here. I'm trying to plug the parameters here. So 6 combinations X, which is 0. And then we have P. P, ladies and gentlemen, here happens to be 0.4 raised to X, which is 0, times, ladies and gentlemen, 0.6 raised to the balancing power. We know that the 2 powers must always add up to this. So the balancing power is N minus X. So the balancing power here automatically will be 6 like that. So please get out your calculator and evaluate this. So what will we get at the end of the day? It will be 6 combinations 0 times 0.4 raised to power 0 times 0.6 raised to power 6, which at the end of the day gives me quite a small probability, 0.0467 like that. Now from there we have probability of X equals 1. I can simply pick the one that we had obtained somewhere here and plug it in there, but because here we are not fighting against anybody's time, I can come and write. So we have 6 combinations 1 times 0.4, I'm plugging in here, 0.4 raised to X, which is 1, times 0.6 raised to power 5, because the 2 powers added together will always give us what here? 6. So get again out your calculator. So we have here 6 combinations 1 times 0.4 raised to positive 1 times 0.6 raised to positive what here? 5, which at the end of the day gives me 0.1866 like that. And then now we have probability of X being equal to 2. So this will be 6 combinations 2. I hope you are able to follow. 6 combinations 2. We have probability of success, which is 0.4 raised to power 2. Raised to power 2. 0.6 this time around will be raised to power 4, given the concept of balancing. The 2 powers must always add up to what? The 2 powers must always add up to the N like that. So then this gives us 6 combinations 2 times 0.4 raised to power 2 times 0.6 raised to power 4, which at the end of the day gives me 0.31104. So what you need to do is to come and give us the total there, because or means what you are adding. So please come and add there. So plus 0.1866 plus 0.0467. So please give us a figure here, which will be 0.54434, something like that. And that is the probability of X being at most what here? At most 2. So that is it. That is it. I can see this figure is not very clear there. So the figure, this figure, can write it here. It's supposed to be 0.54434, like that. That is the probability of at most what here? At most 2. At most 2. And then now we can embark on the journey of tackling the last one. Want now to tackle the last one. The last one, ladies and gentlemen, what do they want us to do for the last one? For the last one, what they want us to do for the last one is quite a simple thing. The last one, ladies and gentlemen, which is Roman 4, they want me to give them 3, probability of 3 or 4 households were affected. So probability of X being equal to 3 or what? 4. So not a problem. These are very easy. I'll be able to handle them separately, and then I add them up. So probability of X being equal to 3. This will be n is still 6, combination 3 times 0.4 raised to X, which is 3, times 0.6 raised to the balancing figure. Given that the 2 powers must add up to 6, then the balancing power will be 3 there. And then I'll come and look for probability of X being equal to 4, which will be 6 combinations X, which is 4 times 0.4 raised to 4 times 0.6 raised to 2, like that. So ladies and gentlemen, what now you'll need to come and do right away is to have your calculator and of course evaluate this. So this will be 6 combinations 3, the first one, times 0.4 raised to power 3 times 0.6 raised to power 3 again, which gives me 0.2765. And then we have here 6 combinations 4 times 0.4 raised to power 4 times 0.6 raised to power 2, which gives me 0.1382. So please come and add the 2 because of the word what here? Or. So we have plus 0.2765, which gives me 0.4147, like that. 4147. So ladies and gentlemen, in my next revision class, I'll be looking at the binomial, not binomial, but the normal probability distribution and the exponential, those 2 only. The normal and what here? Exponential. Otherwise, thank you very much. It has been a pleasure having you around here. Don't forget that we are giving you this class from RCM College, which is the best college for online classes that happens to also publish great books. Should you want to reach out to us, please, this is our number. This is our number, 0719 525 1000. 0719 525 what year? 1000. Otherwise, thank you very much. Bye-bye.